a NASA satellite measured 3 faint bumps in a curve and used them to predict the exact positions of 6 more bumps that no instrument had ever seen. 9 years later, a European telescope pointed at the same sky found all 6 of them, sitting precisely where the arithmetic said they had to be. No other theory of how the universe grew can do that, and the whole prediction rests on a single image, a map of the oldest light there is, a map you could, in principle, build yourself on an ordinary laptop. That light has a name. Cosmologists call it the cosmic microwave background, the CMB, though an older phrase for it simply means relic radiation, the radiation left over. It is the single most important photograph humanity has ever taken, and it is not a photograph of a galaxy, or a star, or a nebula. It is a photograph of the entire sky at once, at a single instant, when the universe was 380,000 years old. Before that instant, the cosmos was an opaque fog of charged particles, and light could not travel in a straight line without being scattered. After it, the fog cleared. The first light streamed free, and it has been traveling toward us ever since, stretched and cooled by the expansion of space, until today it arrives as microwaves, barely a few degrees above absolute zero. Here is where a persistent misconception needs to be set aside, because almost everyone meets this light through a myth. Many people assume the microwave background is a picture of the Big Bang itself, the flash of the beginning, the first moment. Others have heard the opposite, that it is just the combined glow of distant stars, or that cosmologists simply invented it to prop up their theories. None of that is right. The relic radiation is not the beginning. It is a wall, the surface of last scattering, the earliest moment the universe ever became transparent, 400,000 years downstream from the start. It is not starlight, because the first stars would not switch on for another 100 million years. And it was not invented, as we will see, because we can test it 3 separate ways, and it passes every one. What the map actually shows is not the Big Bang, but the seeds of everything that came after it, the faint temperature ripples that would grow over billions of years into galaxies, into clusters, into us. So look at the map. It is an oval, the whole celestial sphere flattened onto a page, and it is covered in mottled patches, hotter spots and colder spots, painted in false color, differences so tiny they amount to 1 part in 100,000. Those patches are not decoration. They are the reason anything exists. If the early universe had been perfectly smooth, perfectly uniform, matter would have stayed spread out forever, and gravity would have had nothing to grab. There would be no stars, no galaxies, no observer to look at the map. But the universe was not perfectly smooth. It had lumps. And those lumps are what we see as spots. Why are there lumps at all? Because everything we see around us today is lumpy. We are a lump. The solar system is a lump. The galaxy, the globular clusters, the clusters of galaxies, all of them are concentrations of matter, denser than the space between them. The whole cosmos, on the scales we live at, is a kind of web, threads of matter strung between vast empty voids. And matter interacts with light. Where matter piled up, it left its fingerprint on the photons passing through, warming some regions, cooling others. The spots on the CMB are that fingerprint, frozen at the moment the light broke free. Zoom out far enough, though, past the clusters and the filaments, and the lumpiness fades. On the very largest scales, the universe becomes smooth again, matter spread evenly in every direction, an almost perfectly even sky. The structure lives in between. Now comes the first genuinely strange idea, and it is worth slowing down for. The biggest patches on the map are the oldest. That sounds backward, so hold on to it. The gigantic blobs, the ones spanning 10 degrees of sky or more, were seeded in the very first instant of the universe, at the end of a fleeting era called inflation, something like 10 to the minus 35 seconds after the beginning. Back then, those seeds were microscopic. But the universe stretched and stretched, and what was once the smallest ripple got pulled across the entire sky. So if you want to see the birth of the cosmos, you look at the largest features. And the smallest patches, this is the part that surprises people, the tiniest spots on the map, only 5 or 7 minutes of arc across, are often the signatures of galaxy clusters, enormous assemblies of matter that happen to sit so far away they shrink to specks. Thousands of those little dots are clusters or the cold, empty voids between them. Big means early. Small means often, near, and late. The map is a record of scale and of time at once. There are, in fact, 3 of these maps, and they look almost identical except for one thing: resolution. One resolves features down to 7 degrees, another down to about a degree, the sharpest down to 5 arc minutes. Each resolution reveals a different layer of structure. The way squinting at a coastline shows you bays while a sharp photograph shows you individual rocks. The coarse maps show the ancient giant blobs. The fine maps show the recent small ones. Same sky, different eyes. To actually do the science, though, the map itself is not what you work with. This is a subtlety that trips people up. You do not analyze the picture directly. You transform it into a curve. The curve is called the angular power spectrum, and it answers a simple question asked at every possible scale. How much energy arrives from the sky at this particular patch size? You pick a scale, say, patches 10 degrees across, sweep the whole sky, add up all the temperature variation at that scale and average it. Then you shrink the scale, sweep again, average again. Do this across every scale and you get a curve. Horizontal axis, the size of the patch; vertical axis, how much the temperature varies at that size, measured in millionths of a degree squared. And that curve has bumps in it, peaks, places where a particular scale carries far more energy than its neighbors. Those peaks are the whole game. Each patch size gets a number, and it is not an arbitrary number. It is a specific integer called a multipole moment, written as the letter Heller's Ella, a small Ellers means a large patch, a broad feature spanning much of the sky. A large Hellers means a small patch, fine detail. When you plot the power against Hellers instead of against degrees, the bumps stand out cleanly. And what causes the bumps is sound. In the hot, early plasma, before the fog cleared, matter and light were locked together, and gravity pulling matter into the seed lumps fought against the pressure of the radiation pushing back out. That tug of war set up oscillations, actual pressure waves, sound waves, ringing through the infant universe. When the fog cleared, those waves froze in place, and the scales at which they had piled up densest became the peaks in the power spectrum. The first peak, the tallest, tells you the geometry of the universe, whether space is flat or curved. It comes out flat, to remarkable precision. The higher peaks encode how much ordinary matter there is, how much dark matter, how fast the expansion runs. This is where the prediction I opened with actually happened. The first full-sky mission was NASA's WMAP, the Wilkinson Microwave Anisotropy Probe. It measured the power spectrum and resolved the first 3 peaks clearly. From just those 3 peaks, the WMAP team pinned down the basic parameters of the cosmos, and then they did something a real theory allows you to do. They forecast where the remaining peaks, smaller scales, higher, would have to fall. Years later, the European Planck satellite measured the spectrum in far finer detail, and there they were, 6 more peaks, exactly at the predicted positions. That is not a small thing. No competing model can produce that many peaks. No competing model, handed the first 3, can tell you where the next 6 will land. Only the standard cosmology, the one built from cold dark matter and a cosmological constant, the model written with a Greek lambda and the letter CDM, makes that prediction and survives it. That is one of 3 proofs, and it is worth naming all 3, because this is exactly how you answer the person who says the relic radiation was invented. The first proof is the peaks, 3 measured, 6 predicted, all 9 found. The second is the sheer existence of so many harmonically spaced peaks, a pattern that falls naturally out of sound waves in a hot plasma and out of nothing else. And the third is the most elegant, and it hides inside something called the Sunyaev-Zeldovich effect. When a photon of the background light passes through a galaxy cluster, it runs a gauntlet of ferociously hot electrons. Those electrons, moving at enormous speeds, occasionally collide with a passing photon and hand it a kick of energy, a process called inverse Compton scattering. The photon comes out bluer, shifted to higher frequency. So in one band of the spectrum, you see a dip where the cluster stole photons away, and in another band, a corresponding rise where they piled up. The size of that dip and rise lets you measure the temperature of the background radiation at the cluster's distance. And here is the payoff. When you look at clusters farther and farther away, deeper into the past, the temperature of the relic radiation rises. It climbs in exact proportion to 1 plus the redshift, precisely the law the expanding universe picture demands. The light was hotter long ago because the universe was smaller. You can watch it cool across cosmic time. That is not something starlight could ever fake, and it is not something a fabricated theory would predict correctly by accident. Now, back to that power spectrum, because it carries a second lesson that is even stranger than the first. Along the curve, especially at the large scale end, there is a band of green shading, a built-in fuzziness the data can never shrink below. It has a name, cosmic variance, and it comes from a fact about our own situation that is almost philosophical. The temperature ripples were laid down by quantum fluctuations, and quantum fluctuations are random. They follow a statistical pattern. On average, the ripples of a given size have a certain strength, but any single realization scatters around that average. Some spots come out stronger, some weaker, and on the largest scales there are only a handful of spots in the entire sky to average over. With so few, the average is uncertain. You cannot beat it down by building a better telescope, because the problem is not your instrument. The problem is that we have exactly one sky. Think about what that means. If we could pick ourselves up as gods, the lecturer liked to say, as beings who set the rules and watch the universe unfold, and drop ourselves a billion light years away and measure the power spectrum from there, we would not get the same curve. Close, but not identical. We would be looking at different spots, a different random draw, average over every possible vantage point in the universe, and you would get the smooth, ideal curve. But we are stuck at one address, seeing one particular set of ripples, and that limits how sharply we can ever know the largest scales. And now the beautiful part. There are two completely different ways to imagine averaging away that randomness. 1. Keep the laws fixed and move yourself to every location in this universe, collecting a different view from each spot. 2. Stay put, but imagine building the universe over and over, infinitely many universes, each with the same statistical rules, each a fresh random draw, and average across all of them. Common sense says these are different exercises. They are not. They give the same answer. This property has a name. Ergodicity. It says that for a certain special kind of random process, a Gaussian process, the kind quantum fluctuations produce, the statistics you gather across space, are identical to the statistics you gather across the ensemble of possibilities. Picture the static snow on an old, untuned television. Take a single horizontal line and watch how it flickers over time, measuring its average and its spread. Then, in a single frozen frame, scan the noise across the whole screen and measure its average and spread across space. The two come out the same. That is ergodicity in miniature. For the universe, we swap time for the number of universes. Measuring within our one cosmos, we can say what an infinity of cosmoses would look like, because the Gaussian character of the primordial seeds propagates through everything. This is the medium we live in. It is why one sky can, in principle, speak for all of them. There is a piece of pure mathematics underneath all this, and it is more approachable than it sounds. Any smooth, continuous shape, Any function can be built up as a sum of simple waves, sines and cosines, each with its own amplitude. This is the idea of a Fourier series. Add a few waves, and you get a crude approximation. Add more with higher and higher frequencies, and the approximation tightens, the wiggles filling in, until in the limit of infinitely many waves you reproduce the original shape exactly. A one-dimensional signal decomposes into sines along a line. A two-dimensional surface decomposes into ripples across a plane. Imagine the interference pattern of sine waves running in two directions, a landscape of hills and hollows. Anything at all, a sound, an image, even, in a sense, a table sitting in a room, can be written as a combination of these harmonic building blocks. The decomposition is unique. There is exactly one recipe of waves that builds a given shape, and no other. And you can run the process backward without ambiguity, from shape to waves, and from waves back to shape. Now take that flat, two-dimensional pattern and wrap it onto a sphere, because the sky is a sphere, not a plane. Something has to change. On a flat sheet, you can chop the wave off at the edge. On a sphere, there is no edge. Go all the way around and you must come back to where you started, the wave closing seamlessly on itself. So the building blocks are no longer flat sines and cosines. They are their spherical cousins, patterns of hot and cold laid across the surface of a ball. These are the spherical harmonics. And here is the plain language translation that demystifies a piece of jargon you may have heard. A spherical harmonic is simply a sine or cosine drawn on a sphere. When physicists say multipole, dipole, quadrupole, octupole, they mean nothing more exotic than these. The dipole is the sphere split into one hot half and one cold half. The quadrupole divides it into 4, the octupole into 8. Each step up doubles the number of patches and halves their size, and the label Heckerot exactly which harmonic you are on. Any map on the sphere, the CMB, or any image, or any pattern at all, can be broken down uniquely into a sum of these spherical harmonics, each multiplied by its own coefficient. The coefficients carry 2 indices. The first Israelik is the multipole number, how finely the sphere is chopped. The second, M, is the mode, the particular way the patches for that multipole are arranged on the sphere. The orientation of the pattern. Together they specify each building block completely, and here is the crucial move that turns a picture into physics. When cosmologists talk about the energy in the power spectrum, they do not mean the raw coefficients. They mean the coefficients squared, averaged together for each multipole. You take the map, clean it, decompose it into spherical harmonics, read off the amplitude of each, square those amplitudes, average them scale by scale, and that average, plotted against her script, is the power spectrum. Astronomers get a map, strip out the noise, expand it in harmonics, and square out drops the curve that hands you the composition of the universe. Which raises a fair question. How do you strip out the noise when the sky is crowded with foreground contamination, the glow of our own galaxy, synchrotron radiation, free emission, warm dust, the carbon monoxide gas that drapes across the Milky Way? The relic light hides beneath all of it. The answer lies in 2 signatures the background radiation carries that nothing else does. First, it is the same temperature in every observing frequency. The CMB looks identical whether you photograph it at one microwave frequency or another, because it is very nearly a perfect blackbody, the purest thermal glow in nature. Foregrounds change with frequency. The background does not. Observe the sky in 9 frequency bands at once, as these missions do, and the component that stays constant across all 9 is the relic light. Second, it is a random Gaussian field with no resemblance to anything else. When you cross-correlate it against other possible patterns, the similarity drops to 0. Those 2 properties together let you write down a system of equations and solve for the clean map, pulling the oldest light out from under the galaxy's glare. And this is where the lecture turned from watching to doing, because the remarkable thing is that you can run the whole machine yourself. The power spectrum depends on a small handful of cosmological parameters, 6 of them, and from those 6, every other number about the universe can be derived. So here is the procedure the students were handed, and it is worth walking through because it is the entire method of modern cosmology compressed into an afternoon. First, you go to a public cosmology tool hosted at NASA, an online program that takes cosmological parameters and returns a theoretical power spectrum. You dial in the densities: ordinary matter, cold, dark matter, the dark energy term, neutrinos. You set the Hubble constant, the expansion rate. You ask for a few thousand points along the curve. Click Compute, and out comes a spectrum, the fingerprint of the universe those particular numbers would produce. But a spectrum is not a map. To turn the curve back into a sky, you need a second step, and you need to inject that cosmic variance we discussed, the random scatter of the vacuum. There are software packages built exactly for this, packages that tile the sphere into equal pixels and let you compute the delicate integrals precisely. The one the lecturer favored has a curious name born of pure mathematics. It uses Gauss-Legendre pixelization, a way of choosing the sample points on the sphere so that the integrals come out not approximately but exactly. The trick descends from a paper Gauss wrote in 1814, the idea that if you evaluate a function at exactly the right special points, the points defined by the zeros of Legendre's polynomials, you can integrate it with no error at all. You do not need to understand the machinery to use it. You feed it your spectrum, you pick a random seed, a number that plants the particular quantum draw, universe number 6 or 7 or any you like, and the program grows a map. If you fix the seed, you can reproduce your universe exactly. If you leave it free, the computer grabs the system clock down to the millisecond and plants a seed you will never recover, and the map it grows can never be made again. Just like our own sky, whose random seed we will never know, there is a resolution rule worth knowing, because it is the same rule that governs digital sound and digital images. It comes from information theory, the sampling theorem associated with the names Nyquist and Shannon and Kotelnikov. The most detailed wave you can capture on a grid of endpoints is the one that fits into n divided by 2. Ask for more detail than your pixels can hold, and you get nonsense. So the highest multipole you can trust is set by how finely you have tiled the sphere, and every other resolution choice follows from that one number. Coarse pixels, blurry universe. Fine pixels, sharp universe. You set the rules of your own game, then you become a cosmic experimentalist. You build one map for the standard model, lambda CDM, the real universe's recipe. You change one parameter. Say you slow the expansion, nudge the Hubble constant down, telling your universe to grow a little more gently, and you build a second map from the same random seed. So the only difference between the two skies is the physics you altered. Then you subtract one from the other. A single command differences the maps, and where they disagree, the discrepancy lights up. Run it, and you see the change concentrated at particular scales for the Hubble constant at the smaller scales, where the expansion rate does its work on features that had time to grow just after inflation. Change the density of dark matter instead, dial it up toward the density of ordinary matter, rebuild the map, and a different pattern of differences appears. You are, in the most literal sense the software allows, running universes and reading off what each choice does to the sky. And you cannot cheat the bookkeeping. The parameters are chained together. You cannot move one and hold the rest still. Push the density of visible matter up to half of everything, and the sum of all the components, visible matter, dark energy, overshoots 100%. And the universe is no longer flat. If you insist that it stay flat, the total energy must add to exactly 100%, so something else has to give way. Change one number and another shifts to compensate. That constraint is not a bug in the exercise, it is the real structure of the cosmos, the reason 6 numbers, and not 60, are enough to describe everything. They are not independent knobs. They are a locked system, and the locking is itself a discovery. There is one more wrinkle, a small technical fork that confuses newcomers when they first draw their own spectrum. Astronomers work with two versions of the same curve. In the raw version, you plot the squared coefficients directly, call it C sub L, and the curve sags downward at small scales, the high L end drooping toward the floor. In the second version, you multiply each point by times luck plus 1, which lifts that drooping tail up and turns the sagging line into the familiar landscape of peaks and valleys everyone recognizes. The two are the same physics, just dressed differently. So if you build your own spectrum and it looks like it is sliding downhill instead of rippling, nothing is broken. Multiply through by that factor and the peaks rise into view. It is worth remembering how much machinery stands behind a single clean curve, because the smoothness of the result hides the violence of the computation. To reduce the raw data a satellite streams down, you do not use a laptop. You need real supercomputers, if only because holding one channel of observation in active memory can demand a terabyte. And there are dozens of channels, several detectors reading the same frequency at once, plus polarization, all of it processed live, in memory, not on disk. Stack those channels and you already have a serious computing system just to convert what the spacecraft saw into something you can look at. The 9 frequency maps that yield the relic image are distilled from tens of raw channels, cleaned, combined, and only then handed to the harmonic analysis. The reason the student's version runs on an ordinary machine is that they skip all of that and start from the finished spectrum. But the finished spectrum itself is the output of a computational effort most people never see. It helps to know what those 6 numbers actually are, because they are fewer and stranger than most people expect for a thing as large as a universe. There is the density of ordinary matter. Everything made of atoms, every star and planet in person, which turns out to be a small slice of the whole. There is the density of cold, dark matter, the invisible scaffolding that outweighs the ordinary stuff several times over and whose gravity did most of the work of pulling the seed lumps into galaxies. There is a number describing the primordial ripples themselves, how their strength changes from large scales to small. There is the thickness of the fog. Technically, the depth of scattering the light had to climb out of once the first stars began to reionize the gas. There is the overall amplitude of the fluctuations, how loud the primordial ringing was, and there is the expansion rate, the Hubble constant, the pace at which space stretches today. 6 dials. From them, the analysis derives the age of the universe, its geometry, the fraction that is dark energy, the temperature history, the works. That such a short list suffices is not obvious and was not guaranteed. It is one of the quieter shocks of modern cosmology that the entire observable universe can be captioned in 6 figures, and there is a genuinely playful side to the machinery, the part that makes the abstraction concrete. Once you have the software drawing maps, you can ask it to draw a single mode in isolation, not the whole sky, but one harmonic, one multipole by itself. Type the key for multipole 4, and the program renders exactly that pattern, the sphere carved into that many patches and no more. You can go further and pull one specific mode out of a multipole, extract, say, the third arrangement of the quadrupole, and the software draws that one building block alone, reading it off the same coefficients it computed for the full map. This is where an important property becomes visible with your own eyes. The modes are orthogonal. Remove one from the sum and the others do not budge. They do not lean on each other. Each carries its own independent piece of the pattern, and the full map is nothing but all of them added together, each with its own weight. That orthogonality is why the decomposition is unique, and why you can subtract, isolate, and recombine the pieces without the whole thing collapsing into ambiguity. It is the same reason a chord can be broken into separate notes and put back together without loss. There is even a small aesthetic confession buried in the method. To view the maps, the packages convert the sphere into an image file, and the conversion is not done with a mouse. It is done by typing keys at a command line, the way astronomers have always worked, flags and switches strung together, no clicking. You can rescale the contrast, view the same data stretched from a narrow temperature range, where every faint spot leaps out in violent color, or from a wider range, where the contrast softens and the map looks almost calm. Same numbers, different skin. You can lay coordinate grids over the sphere, galactic, ecliptic, equatorial, to orient yourself against the Milky Way or the plane of the planets. None of it is strictly necessary to get the science, but all of it is part of learning to feel the data as an object you can turn in your hands, rather than a result handed down from an authority. And that, in the end, is the whole point of putting the tools in a student's hands. You do not take the relic radiation on trust, you build it. Stand back from all of it, and here's what the exercise leaves you with. A single map of the sky taken when the universe was 380,000 years old contains encoded in the sizes of its blotches, the geometry of space, the amount of ordinary matter, the amount of dark matter, the pace of the expansion, and the character of the primordial seeds that grew into everything. The map becomes a curve. The curve becomes 6 numbers. The 6 numbers regrow the map, and you can run that loop by hand, building universe after universe, differencing them, watching how the sky answers when you change the rules until you understand, not on faith but by construction, why cosmologists say they know how the universe is built. They know because they have the CMB, and because when you hand the model the first 3 peaks, it tells you where the next 6 will be, and the next 6 are there. It took more than 1,000 tries. The lecturer admitted to get every piece of the analysis to line up. But it did line up. Our universe came out, and the map of its first light, once you learn to read it, turns out to be legible after all.